Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Nianyi Chen with us today. Hello, Nianyi.
Hi, everyone. I'm Nianyi from Carnegie Mellon University.
Cool. And where is Carnegie Mellon?
It is in Pittsburgh, Pennsylvania.
Very cool. Pittsburgh. And it is September 18th of 2023 as we record this. So are the trees starting to turn colors there in Pittsburgh? Not quite yet?
Not yet, but maybe in like a couple of weeks it will. But the weather is definitely a lot cooler, like starting from last week.
Nice. Yeah.
Yeah.
I'm in Phoenix, and even we are starting to cool down a little bit.
Oh, that's very nice. I heard that Arizona is very hot.
Arizona is always very hot. But yeah, we did cool down. We're still hitting triple digits. We're still in the hundreds, but it's a dry heat, as they say, and it's pretty livable. So all good. Very cool. And Nianyi, what's your position here at Carnegie Mellon?
I'm a final year PhD student, so yeah, I'm about to graduate. I'm looking for postdoc positions, which makes it stressful times for me. But yeah.
There is a pitch, people. So if you've got a position, make an offer. Well, that's really great because I can look forward to saying Dr. Chen. Hello, Dr. Chen. It's close enough. We'll go. And Dr. Chen, what do you like to do for research?
So most of my research involves numerical simulations, like as a theoretical tool for understanding the evolution of the universe, of galaxies, and the interaction between black holes, for example. So recently, my interest has been mostly around like supermassive black holes, evolution in their host galaxies, and their interactions with each other when galaxies merge.
Cool. Very cool. And that is going to bring us to this very lovely APJ letter. It is open access, people. It's the open access era. You can go get a copy for free. Go get one. Flyby, galaxy encounters with multiple black holes produce star-forming linear features. And Nianyi, take us away.
Yeah, so this is our recent work based off of a very exciting observation. And so this work is done with the ASTRID simulation team. We have a lot of ASTRID people on it who've worked very hard to make this simulation happen and allow the analysis that happens in this paper in particular. And also we have a theorist, Priya Natarajan, who's also part of the original observation paper, and it's good to include her in this work because it's a good collaboration between the original observation team and the simulation team who follow up on this objects.
Very nice.
So yeah, the observation that motivate this work, I think is out this March. So it's this Van Dockum 2023 VD23 paper who make a very exciting and serendipitous discovery of this very rare, very bright and thin stellar streak that is like very long, like 60 kpc is kind of a lot larger than a galaxy size. It's like a few tens of times the size of a galaxy. So they while they were observing, they identified this like very stray, very thin but bright object from the universe, from within their observation field. And so that's like a very rare phenomenon. So like they want to understand better what might produce these very rare objects that they see on the sky. So in the original observation paper, they come up with a lot of very interesting theoretical interpretation of the object. And one of which is that these objects come from the interaction between 3 massive black holes. And when you have 3 massive black holes, they can go through like very chaotic motion, you know, like this three-body encounter can be very chaotic. And then eventually they propose that maybe one of the black holes get kicked out of the original galaxy
Yep.
During this interaction. And then when it gets kicked out, it gets kicked at such a large velocity, it will interact with the surrounding gas,
Cool.
Gas medium, and also it might carry around it a stellar cluster that like that produce this whole linear feature that's seen on the sky.
Cool.
So that's one of the very interesting proposal that they made. And this is also like theoretically very compelling because like, yeah, like three-body interactions are just very interesting things to study. And when you, and it also offers like very novel ways of observing black hole. If this is true, then maybe we can look for like black holes out of their host galaxy just by looking for these features.
Yeah.
So it's definitely like very compelling theory.
Nice.
So actually, so when we look at the paper, I'm actually I was actually working with an undergrad specifically on triple massive black hole encounters using the simulation at the time. So so then we started to look into this phenomenon among the triple black hole interaction candidates in our simulation. So yeah, so that's the background for this work. And so we want to see, for example, first whether the proposed scenario by the observation team is something that we can find in our simulation, like whether we can find these type of stellar streak from three-body encounters.
Cool.
And then also another question is like, are there other scenarios that might be responsible for these type of features? So these are the key questions that we want to study with this paper.
Nice. Should we jump down maybe to figure 3 at this point?
Yeah, so I think figure 3 is a good illustration of the very exciting observation that was made. So this is the observed system, and on the right is this linear, very straight, bright linear feature that was seen by the observation team using the Hubble telescope. So you can see it's kind of very bright. So the feature is straight and bright, and it's also blue, indicating that these are very young stars, newly formed stars. And you can see also like there are several knots of bright regions. So these might be associated with black holes, which is embedded in like young and dense stars. And the galaxy on the left is like at the same redshift as this linear feature. So it is believed that the original interaction happens in this yellow galaxy, and then the black hole get kicked out that produce this straight feature on the right. So this is the original observed system.
You remember what the redshift of this object is?
Yeah, so according to the observation team, this is a redshift 1-ish galaxy. So it's pretty far from us.
Yeah. Okay, very good.
Yeah, so then we begin our search in the simulation. So we can go to figure 1, which lay out a overall view of our simulation data that we start our search from.
Okay, here we go. Figure 1.
Yeah.
Galaxies.
Yeah, so we use the asteroid simulation, which is a very large volume, high resolution cosmological simulation with black hole and star formation, galaxy formation physics in there. We use that as a ground for searching for these theoretical counterparts of the observational systems.
Cool.
So in this figure, we lay out the entire galaxy and black hole population. And we have, because the simulation volume is so large, we have so many black holes and galaxies that we might be candidates for this search. So what we did first is to make some cuts on the data so that we know exactly what kind of galaxy, what kind of black hole population we're targeting among the massive amount of data.
Okay.
So what we do here is we try our best to match the properties of the observed galaxy and black hole mass estimation based on the original observed paper, because they have some estimation, for example, for the galaxy mass and for the star formation rate based on the light emission from that galaxy.
Okay.
And also they say this is like a relatively compact galaxy, so that's why we also put constraint on the half mass radius here. So we end up with this orange population, which is like a subpopulation of the original asteroid galaxy.
Yep.
That we use to further search for these linear stellar features.
And what is system 1 and system 2?
Oh yeah, system 1, 2 are eventually the two features that we identify in figure 3. So here we kind of put them here to give you an idea of like where do they lie within these like black hole galaxy relation.
Thank you.
Yeah. And so yeah, we start from this subpopulation, and so as I said, we asked two questions. The first is, because the observation team proposed this very compelling theory of a three-body encounter and a flyby, a kicked out, or they say like runaway black hole, which produced this feature. And we happen to actually have some of these runaway black holes in massive black hole triplets in the simulation. So we start to look for, we start to investigate a little bit these runaway black hole systems and see whether they can produce these kind of stellar features. So this leads us to figure 2, where we show one of the black hole that gets kicked out of this host galaxy during a triple encounter. So here, in the background, I show the galaxy. It's kind of a very busy region where we have like a lot of galaxies come and go in this region. But here, in the center, we have 3 black holes marked by the crosses: the red, the blue, and the green.
Yes.
So they spend time like in the same galaxy. And after about 200 megayear of interaction, you can see this red one, just during this interaction, suddenly get ejected from its host galaxy. So it's kind of no longer embedded in this galaxy, and it get out at a speed of a few hundred kilometers per second during this complex interaction. So this is kind of the object that will in theory create the kind of stellar wake that's proposed by the observation system.
Cool.
However, in this case, we don't really see that it has a linear feature, very, very like star forming linear feature with it. So it's kind of it's, I wouldn't say that like it contradicts with the proposal in the theory paper, because there are definitely limitations for this investigation due to, for example, our simulation resolution. And also it depends on the speed at which this black hole get ejected. So if in some cases, when the black hole is ejected at very high speed, as opposed to this like a few hundred kilometers per second, if it get ejected at a few thousand kilometers per second, maybe there is a chance that it will produce this star forming linear feature. But in our simulation so far, we haven't found any. But we're definitely keep looking, because we haven't studied all of the systems in the simulation, so there is still hope for finding them.
Cool. I have one question on the middle one. Is this sort of a interloper black hole coming in on this particular time shot? This golden.
Yeah, so this is this is a busy region. This is definitely like another galaxy with a black hole embedded that kind of comes along, and maybe it will also merge with the central one, and then it will be like, instead of a triple system, maybe it will be 4 black holes and then even more black holes in these very massive galaxies. Yeah.
Nice. Beautiful.
Yes, so yeah, like our initial search for a runaway black hole induced wake didn't give us the exact wake that's observed. So another thing we did is we asked, if these runaway black hole doesn't produce those feature in our simulation, do we actually see any of the feature that might match with the observed system in our simulation? So now, like, we kind of carry out this direct search for this linear feature. We don't, like, for now, we don't care about what produce it, but we just like specifically write an algorithm to look for these very elongated star forming tails or wakes next to a galaxy that's similar to the observed one. And guess what? We do find a few of these systems in the simulation, which is really exciting. Like, I haven't expected that they will have such good resemblance before I go on with this search. But yeah, so in figure 3.
Let's go to figure 3. Back to figure 3. So we have our observed, and then
yeah, so in figure 3, we showed 2 of the systems that we found in our simulation, system 1 and system 2, that like stand out during our search for the linear feature, and then we realized that they match very well with a few properties of the observed system. So first, like visually, they actually look very linear, and they have these like bright dots next to a compact galaxy, like a extended linear feature with similar length of the observed system. And they're also quite bright, and they're also star forming. Like, this entire linear feature is star forming. So and the third row is like a visual comparison of our system as it will be seen in the HST Hubble telescope, as opposed to the original image of the observed system. So we see, like, visually it's already obvious that they resemble each other in a lot of ways.
And
then it's also proposed that, like, if we see these star forming features, there might be like a lot of cold dense gas that like leads to these new form stars. So then in the simulation, we have full access to all the environment of the system. So we further look at the surrounding gas environment for this feature in the second panel, and we see this pretty striking stream of cold dense gas that sticks out of the background, which we think is responsible for producing this this very dense star formation that produced the linear feature. And also we see that embedded in this feature, in both of these features, we see 2 black holes interacting with each other. Which is even more interesting. So in some sense, this is like a triple black hole system, but it's just not exactly the original scenario of a runaway black hole. But we do see like a triple interaction of some sort in this system, which we think is very exciting.
This is more like a hierarchical triple, right? You got a tight binary with a third one on the outside.
Yeah, so yeah, this binary kind of forms, and then eventually it will merge into the left galaxy, as we'll see later. But yeah, so then we see, like, visually this system actually resembles the observed one very well. So we then go through a few more quantitative analysis to actually mock this system in terms of the like different wave bands in the HST. And then so that leads to the fourth panel, where we kind of map out the stellar age along this feature, and then also the associated emission in this F606 and F814 bands, which is kind of a way people use to select out these newly formed stars. We see that in the stellar age, for example, there are some very young stars in this population below 100 mega years in age. So they will be responsible for emitting those kind of bright blue lights along this feature.
Love it.
And this actually also, when we compare this plots to the original observation, they actually match quite well in a lot of properties.
Nice.
So we think like the scenario, based on our comparison and this analysis, we think that this system resembles the observed system in many ways. And so we propose that this could be another way that might be the theoretical explanation for the observation of a linear feature.
Very cool. Very cool.
And so yeah, another question that we explore is, so yeah, like based on the single observation, actually we can stay at figure 3 for a bit more. Okay. Yeah, because I want to go through the last panel.
Oh, good.
So yeah, like now we seem to have different theoretical explanation for this observation. Like, how do we know which one is correct? Like, how do we distinguish between them? So I think one way that might help distinguish between the runaway black hole scenario and this flyby encounter scenario is that in the scenario of a flyby galaxy encounter, because there is actually a galaxy along this stellar streak. So the galaxy will have a bunch of old stars together with the young stars, which will actually be able to tell that the flyby encounter galaxy is the case or not. Like, for example, if in the future JWST observation of the system, we do see a few old stars, not a few, like we do see the old stellar population appear as the red one in here, then maybe we can say, oh, this is actually a flyby encounter scenario as opposed to a runaway black hole scenario. But if we don't see this old star population, then I would say that the proposed runaway black hole induced linear feature is like really compelling. So it can provide further evidence that this is a runaway black hole induced star feature. Yeah. So yeah, so because we have, like, in a simulation, we can not only look at this one snapshot of information, and we have like an entire time evolution of everything of the system. Right. So we decided to take advantage of that and to analyze a little bit how the system evolved into the final stellar feature, and then after the feature form, what will happen to the system. Nice. So in figure 4.
Slide on down. Evolution of the linear feature. Yes, let's take a look at that. Okay, so I'm going to zoom out a little bit so we get a global here. Okay.
Yeah. Thanks. So in figure 4, we kind of traced the system across the time before and after its formation. And we also choose to rotate the viewing angle of the system so that it's kind of like a face-on projection of the system. So compared to the figure 3, you actually see these galaxies like more in a flatter view.
I'm with you.
And you see kind of like how they pass by each other and how this blue region of new stars start to stretch. So yeah, it starts with like a dense galaxy and a very young blue smaller galaxy that just went through like a binary merger. That's why it has two black holes within it, and that's probably also why it has so much like star forming gas and young stars within it. So you see, like when they pass by, they go through this very interesting orbit where like they barely touch each other, but they don't completely disrupt each other. So the like all the stars in the blue galaxy is still retains itself. It doesn't get disrupted, but then it get this tidal stretch from the compact galaxy, and this tidal stretch kind of result in this like tidal arm kind of feature that we see that will be observed as the linear feature. So you see this arm extend like really long, up to like a few tens of kpc in length.
Okay.
So yeah, so after like the time when we capture this linear feature, you see like it keeps extending a little bit more, and then the stars kind of gets older. So that's frame 5. You see like those stars turns from blue to red, meaning that it gets older.
Yes. 409.
And then finally this galaxy comes back to the original compact galaxy and merge into it. And so this merger also triggers a lot of star formation in the compact galaxy. So it kind of appears as blue after this galaxy merger. So in the merger remnant, we see like the 3 black holes begin to interact with each other. So it's kind of also like a scenario of a triple black hole interaction in the final merger remnant.
Very nice. Okay, I'm with you.
Yeah, so because I'm interested in like black hole interactions and like how we can detect those triple black hole systems. So we go on to investigate like so the original observation focuses on the galaxy, but it's also interesting to look for the emission from the black holes inside the galaxy, because black holes can be detected as AGNs because they emit light in the X-rays in the
high energy.
So yeah, so we then investigate like, oh, if we have this system, this like triple black hole system along the linear feature, if we look for the black hole emission, can we actually see the black hole along with the galaxy inside it? Like how strong is the black hole emitting? Is there a chance that we might detect some of it?
Good.
So this leads us to figure 5, where we investigate a little bit of the properties of this 3 black holes embedded in this linear feature. So here black hole 1 is still in the compact galaxy, and 2 and 3 are the ones along the feature, which are smaller. So we make predictions for the masses and luminosities of these black holes in the system. So
luminosity. Okay.
yeah, so the black hole mass of the larger galaxy in the of the larger black hole in the compact galaxy is actually quite massive. It has massive 10 to the 7 solar masses, which is kind of what we expect of a galaxy of this mass, and it's also similar to the proposed black hole mass in the original observation paper. And then we have 2 black holes interacting and embedded in the feature, and these are smaller black holes of mass from 10 to the 5 to 10 to the 6 solar masses. So we then look at whether we can see those black holes by investigating their X-ray luminosity. That's how we might be able to observe them in the X-ray. So they're actually quite, at least 2 of the black holes, the blue one and the green one, they're quite bright in the X-ray band, and this is definitely something that has the potential to be observed by current and future telescopes if we look at that system, and we might be able to actually see the X-ray emission, which is quite exciting because if we see the black holes and if we see black holes along the feature, then
Yes.
it is definitely like a way to say, oh, this feature is associated with a black hole in it, and maybe in the future, by looking for these features, we can also tell something about the black hole interaction of these complex systems. Yeah, so I think this is like very exciting things that observations will be able to look for to associate black holes with these linear features.
Yep, multi-wavelength.
Yeah.
Good, very good. Very cool.
So yeah, so this kind of ends our investigation of this system. Yeah, so our key conclusion is that according to the simulation, we do not see that runaway black hole produce these linear features, but the exciting thing is that we do find actually more than these two systems of linear features within the simulation. And we think it opens up like a very interesting area of study of like what would produce these linear features and whether we can associate multi-black hole interactions with these linear features. Yeah, and we also use our simulation. We propose this scenario of a multi-galaxy flyby encounter, which we think, according to the analysis, is the most compelling scenario for producing the observed systems.
Yeah, very cool. Very nice. Very nice. Beautiful. Nianyi, I want to thank you so much for walking us through your very lovely APJ letter. Very cool. And you touched on it a little bit at times as you went through. So let me push on it a little bit. So where do you think we go from here, given the published article? Is there already proposals to do in the pipes to do X-ray observations? Maybe there's other wavelengths or other energies to look at. Is there additional theoretical work to be done? Just sort of next steps, what you think we go over the next, say, 2 to 5 years?
Yeah, I think there are definitely a lot of things that we could do following up this work. I think like based on my understanding, I think the original observation team already proposed a lot of observation in other bands of the system because it's so rare and it's so striking to see this feature. So I think they have some radio observation of the system, which kind of also support their claim that like these host galaxy and the feature are actually the same system. They're not like projected to be near each other. And also, as we also hinted in this paper, I think it would be very exciting to look at the system from JWST because it can use the radar bands to actually see whether there is an old stellar population or not. That will help distinguish between the different formation scenario for the feature. And on the theoretical side, because I work on simulation, I think there are also a lot of things that could be done to further investigate the origin of the system. For example, in this paper, we kind of say, oh, like the runaway black hole does not produce these feature in our simulation, but we're also limited by the ejection speed of a black hole of the system, and we're also limited by the actual mass resolution that we can resolve the very dense gas because it's like a huge cosmological volume. So another thing we can do is to, instead of taking like such a huge cosmological volume, we just like simulate this one system, just like shoot a black hole across a gas medium out of a galaxy, and then we can go to very high resolution and we can really see whether like what kind of stellar feature it will be able to produce.
Good. Very good. Sounds like a good postdoc project.
Yeah.
Well, that's good. Well, good. I'm really looking forward to seeing this field evolve over the next couple of years. It'll be very exciting to see
Yeah, it's very
what is the
exciting.
nature of these linear features. Very cool. Very nice. Dr. Chen, thank you so much for
Yeah,
walking us
thanks.
through.
Thanks for listening.
Sure.
Yeah, it's great to present my work here. It's a pleasure. Thanks.
You are welcome. Thank you for doing it. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.